Okay, so we have two questions for formulas and equations. I'm going to number them 1 and 2. Okay, so how do you write formulas for ionic compounds when given their names? So I'm just going to give you guys some examples. Let's do sodium oxide first. Then let's do magnesium nitrate. And copper 2 sulfate. Okay, so first I know that these are ionic compounds because the first thing is a metal and the second thing is a nonmetal or a polyatomic ion. So the process is the same for all three of these guys. You want to write out the symbol for the metal and the symbol for nonmetal. Then you want to go and look on the periodic table to see what the charge of Na would be. So Na is +1 when it's in a compound, and O has a -2 charge when it's in a compound. So I want to write down what each one of them would be. Then you literally take these numbers and crisscross them down so they become subscripts for the opposite element. When you bring the numbers down, guys, you don't have to bring down the signs. Like, you can't have a -2 amount of sodium atoms, so you're literally just bringing down the number. So Na would now have a little 2 next to it, and O would have a little 1 next to it, but when it's a 1, we don't have to write it. So that would be sodium oxide. Now, when you're naming ionic compounds, the nonmetal ending changes to IDE, so oxygen turns into oxide. If you see an IDE ending, it's usually just that nonmetal on the right side of the periodic table. This next one I noticed ends in something different. It ends in 8. So nitrate is one of the polyatomic ions, and you find your polyatomic ions on table E. Okay, so I would look here to know what the symbol for nitrate is and what its charge is. And if you look at the column on the right, about 6 down, 5 or 6 down, nitrate is NO3 with a -1 charge. So I'm going to do this exactly the same. I'm going to write Mg. I'm going to look up its charge on the periodic table. It's +2. And nitrate is NO3 and its charge is -1. When I take these numbers and crisscross them, a polyatomic ion, whenever you have more than one of them, you have to put it in parentheses. So that little 2 that I'm going to bring down is going to go on the outside of the parentheses to show there's 2 of that whole thing. Okay? Now this last one has a Roman numeral in it, and that's because it actually looks scary, but it's actually them trying to make your life easier. If I go to look up copper on the periodic table, copper is one of those transition metals in the middle that has a whole bunch of different charges in the top right-hand corner. So copper can be +1 or +2 when it's in a compound, and you can't just pick whatever you want. The name has a 2 in it because they're telling you in this compound it has a +2 charge. Okay? Again, guys, sulfate is a polyatomic ion, so I would go to table E, look up its symbol, I would look up its charge. Now, the last step after you crisscross your oxidation states is to simplify the subscripts if you can. Anytime you're bringing down 2 of the same number, a 2 and a 2 are going to simplify to a 1 and a 1. So it's as if you're bringing down 1s for both of these things. So you don't have to write the 1s in. I also don't have to put the sulfate, the SL4, in parentheses if there's only one of them. Okay, so you remember you're crisscrossing and reducing. How to tell the difference between different reactions. Okay, so as far as like non-organic reactions go, there's 4 of them that you need to know. There's synthesis, decomposition, there's single replacement, and there's double replacement. So synthesis means that you're taking multiple things and you're combining them together to make one thing. So you have 2 or 3 separate things on the left side of the arrow, but on the right side of the arrow you only have one thing. So anytime you see just one thing on the right side of the arrow, you know it's synthesis. It can't be anything else. The opposite is for decomposition. Decomposition means you're starting with one thing and it's breaking apart into pieces. So decomposition is the only kind of reaction where you have one thing on the left side of the arrow. That would be your only option. Single and double replacement sometimes get confused. Let's say I have a single element and a compound. Now, elements don't like to be alone because they're more stable when they're bonded to something else. So A is going to try to kick B out of the compound to take its place. So A is now bonded to C and B ends up by itself. So A replaced B in the compound, okay? Double replacement is a little bit different because you start off with nothing alone. You start off with two compounds, but the atoms aren't happy in the bond that they're in, so they want to switch places. So like A and C, if they tried to switch places, now A would be bonded to D and C would be bonded to B. Okay, so we still have replacement happening, but if it's double replacement, we still end up with two compounds. Nothing is left all alone. In single replacement, you're going to have a compound and then something always is going to be left by itself. So that's how you tell the difference. Okay, so mole is good, no one has questions. Yes is good, no one has questions. Okay, how do we tell if a solution is supersaturated? So there's two ways you can tell. It depends what the question gives you. I'm going to start by showing you how to use table G. Let's say they give you a temperature. I'm going to say it's 10 degrees Celsius, and I have 150 grams of Ki dissolved in 100 grams of water. Okay, so they're going to give you a temperature and they're going to tell you how much stuff is dissolved. So I'm going to go to reference table G. Okay, and I'm going to find a temperature 10 degrees Celsius, and I want to go all the way up to 150. If you plot that point, where is that point in relation to the Ki line? Is it above it, is it on the line, or is it below it? It's above the line. So anything that you plot on table G that's above the line is supersaturated. So that's one way to tell. The other way to tell is by doing a test. Supersaturated solutions have all of the solute dissolved. So from the outside, you can't tell it's supersaturated because it looks clear. So what you do is you drop in an extra crystal, and if the solution is supersaturated, meaning it's really already holding more than it should, and now you try to put in one more piece and make it hold that too, the whole solution is going to fall apart and you're going to have precipitation occurring. So all the extra stuff is going to fall out. So that's how you would tell it's different there. Okay. Kinetics and equilibrium. Let's see. You know what, guys? This is going to be kind of a long one. These are pretty involved questions, so I'm going to stop here and start a new video.